So a fine steel wire has the force extension properties shown in the figure below. That's good. All right, so there are our questions. Calculate the spring constant for the wire. Okay, so just like I said, the spring constant is the gradient of the graph. But we're looking at the gradient only in the elastic region. Once we go beyond that, our spring constant is no longer constant. Okay, if you have a look at the graph on the previous slide, it gets squiggly after that point. Our constant's not a constant. So our K value only holds for the elastic region. So we need our gradient of our graph. So K is equal to rise over run, which is equal to, so what's our rise, 40? Oh, yeah, that'll work too. 40 over 0.2. Oh, millimeters, yeah, right, okay. Good catch. All right, so what is that? So 20 millimeters, so let's do 20 times 10 to the negative 3. Yep. Oh, let's be careful there. Just seeing if you're all awake. All right, so I get a spring constant of 2,000. A spring constant is newtons per meter. Now, by the way, just quickly, to prove that the spring constant is actually the gradient, if we look at Hooke's law, I didn't explain this before, but F equals Kx, okay? So, therefore, if we want K equals F on X, rearranging. And F on X, F is our rise, X is our run. All right, so K just is our gradient. All right. Calculate the strain potential energy that the wire can store before permanent deformation begins. All right, so that is the energy that it can store up to the elastic limit. Okay? So we need to work out the area under the graph up to our elastic limit. So in this case, it's a nice triangle. So our energy equals the area under graph which is equal to triangle half times base times height, half times, now the base was 20 millimeters. Yeah, so 20 times 10 to the negative 3 times our height was 40 newtons. Okay. 0.47? 0.4. Oh, 0.4. 0.4 joules. I'm happy with 0.4. I didn't double check that. All right. Oh yeah, so half of that is, yeah, okay. Yep, that'll work. Okay. So we've got our energy under the graph up to our elastic limit. So that's before permanent deformation begins. Calculate the work done to break the wire. Okay, so for this, we need the energy under the graph up to our breaking point. So in this case, we're going to have, some squiggly lines. It's going to be really difficult to work out the exact area under that graph. So we're going to be counting squares. All right, so we don't need to count the triangle. We know there's 0.4 joules to this point. But if we look at each square, first thing, work out what each one is worth. So it is 5 millimeters and 10 newtons and 5 millimeters is each square. Okay, so what is that? So each square has an area of 5 times 10 to the negative 2. All right, so if we count our squares up,
so it's negative 3.
I make it 25. 25 after the elastic limit. Maybe 24 and a half. Yeah, so sorry, this 5 times 10 to the negative 2 is because we've multiplied the 10 by the 5 times 10 to the negative 3.
Okay.
Okay, so I'm calling that. We have 0.4 joules under the graph up to the elastic limit. And then after that, I count 25 squares. 25 times 5 times 10 to the negative 2. You didn't get 25? Good. So in total, I get 1.65 joules.
So that's after the elastic limit.
Yes, so that 25 squares is after the elastic limit, because we already know the area under the graph at the elastic limit, so it's just 25 squares after that. Okay, so that's where our 25 has come from here, 25 squares after the elastic limit, but we know before the elastic limit we've got 0.4 joules under it. So let's just put this in brackets to make it a little bit easier to understand. So that 0.4 is up to the elastic limit, that is after the elastic limit.